All right, so now I want to review some properties of vector spaces, the concept of a linear combination, and linearly dependent and independent sets of vectors. So what do we mean by that? So if we can find these scalars, lambda 1 through lambda n, to scale the set of vectors a1 through an such that they can be added up after being scaled to reconstruct the vector b, then we say that B is a linear combination of the vectors A1 through AN. And then this brings into the concept of a linear dependent set of vectors. So we say that a set so if we can find these scalars and they're not all zero, in such a way we can take a combination of the A's and get zero, then we say that the vectors are linearly dependent. So here are some examples of vectors that are a linear combination of others. So if I create the vectors a1 equals to, let's say 1, 2, 0, and a2 equal to 0, 1, 0, and then I find the vector b is equal to 1, 3, 0, then b is going to be a linear combination of a and a2, a1 and a2, because b is equal to a1 plus a2, right? So the two scalars are lambda 1 equals lambda 2 equals 1, right? We can verify 1, 3, 0 is equal to 1, 2, 0 plus 0, 1, 0. So this is an example. So B is a linear combination of A and B, of A1 and B1, A1 and A2. Now I'm going to construct three vectors, or give an example of three vectors that are linearly independent. So, all right, now I'm going to construct an example of three vectors that are linearly independent. So for example, so I claim that these are linearly independent vectors. Okay, to demonstrate that that is indeed the case, we're going to assume the contrary. So if we assume B1, B2, and B3 are dependent vectors, which means that there exists a lambda 1, lambda 2, and lambda 3, not all 0, such that lambda 1 b1 plus lambda 2 b2 plus lambda 3 b3 equals 0, which would mean that lambda 1 times 1, 0, 0 plus lambda 2 times 1, 2, 0 plus lambda 3 times 1, 2, 3 is equal to 0, 0, 0. Or lambda 1 plus lambda 2 plus lambda 3, 2 lambda 2 plus 2 lambda 3, and 3 lambda 3 is equal to 0, 0, 0. Now if the two vectors are equal to each other, then they have to be equal component-wise. So if I take the last component, then this one implies 3 lambda 3 equals 0, so that lambda 3 is equal to 0. Now if I go to the second row, I have 2 lambda 2 plus 2 times 0, because I can back substitute lambda 3, which I already know is 0, has to be equal to 0. And so therefore lambda 2 is also 0. And now if I back substitute in the top row, I have lambda 1 plus lambda 2, which is 0, plus lambda 3, which is also 0, is equal to 0. So lambda 1 equals 0. And therefore this contradicts this assumption for linear dependence. And so if they are not linearly, then they cannot be linearly dependent, and therefore they are linearly independent. So this would be an example. All right, so we'll talk about more properties of vector spaces. If we have a set, so if any vector, so if any vector in B can be written as a linear combination of a set A1, A2 up to AM, then we say that this set spans V. Then the set is said to span V. So in three-dimensional space, the three vectors 1, 0, 0, 1, 2, 0, and 1, 2, 3, they are independent, and they have the same dimension as the space of three-dimensional vectors. So this would be an example of three vectors that span the vectors in R3, the vectors in R3. And in addition, if A1, A2 up to AM are independent, and span V, then we say that the set, the set forms a basis of R3. Oh, sorry, of V. So, for example, these three vectors, they both span V and they are independent, so they could form a basis. An example of a set of vectors that span but could not be a basis are the following example: 1, 0, 0, 0, 1, 0, 0, 0, 1, and then 1, 1, 1. So these four vectors, they also span the set of three-dimensional space, but they are not independent because the last one is the sum of the first three. So if this is A1, A2, and A3, whoops, yeah, A4, and A4 is equal to A1 plus A2 plus A3. Therefore, they are not independent. So even though they span the space, they cannot be a basis. All right, so that concludes this video.